Hey everybody, my name is Brace. I'm an engineer here at LangChain, and today I'm going to be doing a video called LangTool. And this is going to be a walkthrough, a live coding video where I build a program I'm calling LangTool. It's built on top of the Anytool and Toolllm papers that will be linked in the YouTube description. Very interesting. Basically, at a high level, it's using LLMs and RAG techniques to call APIs, given a massive data set of APIs. The data set we'll be using in this video was extracted, I took it from the Toolllm data set, but then slimmed it down to only about 130 APIs instead of the 16,000 that they have in their data set, just so it's a little easier to work with. But the principle is the same. Yeah, so the overall idea is you take a user's query, you want to then extract a category from the user's query. This category, we're going to provide a list of all the categories the LLM can choose from. We're going to be using tool calling, so the LLM can just respond with the tool it wants to, or with the category it wants to use via the category tool. From that category, we can then get a list of all the APIs in our data set with the category. Since we're only using about 130 total APIs, each category doesn't have more than like 3 or 4 APIs, I think. So we just pass all the APIs to the LLM. Here, the LLM then selects which API it believes best matches the user's query. From there, once we have the actual API and the API spec, we can take the user's query again, that API spec, pass it to an LLM, and get a structured response with the different parameters or search params or the body of the API from the query. We then pass that to the next node where we verify that all of the parameters that the API requires we have. If we don't have that, then we go to this is a conditional node. If we don't have all the parameters, then we go to this human in the loop node, which allows the user to type in on the command line the missing parameters they have, or it could be something else you'd expand it to, like in a UI. That then gets sent back to the verify params conditional edge. If we're able to verify all the params are present, we pass it along to the next node, which actually goes and executes the fetch response, and then we have the final result. Yeah, so this is going to be built on top of mostly LangGraph, using LangChain as like the core building blocks, of course, and TypeScript. We're not going to have a UI for this, it's all going to be on the command line, but it should be pretty simple to extend to a UI if you want, or build on top of it to build something else. Alright, so the first step, you're going to want to clone this repository I have. This is just like a template repo. It comes with the dataset we're going to be using, and the backend directory. It's like a TypeScript monorepo, and it has some kind of placeholders, or that's not placeholders, files, and functions, just so we can go through them by one, implement them all, and we know we're not missing anything. So I'll add a link to this, but you're going to want to go in, copy the get URL, clone it, and once you've cloned, you can navigate LangTool. You can navigate in. We're going to want to install dependencies. We're using yarn in this project, so just run yarn. And then if we open it up, we can go to the backend directory where all of our work is going to happen. And the first thing we're going to want to do is add our secrets, just so we don't forget. So optionally, you can add langsmith. I'll probably use it throughout this video to debug if anything goes wrong, and get some great observability and tracing on all of our runs. So you just want to add in your langsmith API key, your project, and then of course your open API key for function calling and all the LLM calls we have here. So you're going to create a .im file, copy this in, add it, and then you're set there. If you look inside our package.json start script, we're pointing our .env configuration at this file. So if you want to name it something else, you just got to update this. And I will do this off camera. But to start, we're going to want to implement our graph. And this will give us the overall structure of what the LangTool is going to do. And then we can go through by one and implement the actual functions. If we go back quickly to the README, or I'll just go to the actual image, then we can see our graph is going to have 1, 2, 3, 4, 5, 6, like 7 nodes. And once we implement all those, we can go through it and implement the actual core functionality. So for LangGraph, you're going to want to first define your graph state and then your channels. And this will be the different state that's passed around to each node. In LangGraph, we have nodes, and then these nodes all have the same state, which is passed through to each one. They all have the same input, so it'll be this state graph. And then when you actually return data, you don't have to return the entire node. You can return one element, two elements, no elements, whatever. And then LangGraph will actually see which elements you returned. It'll then append or replace that in your data in your state and pass it on to the next node. So we are going to have an LLM, which will pass in when we instantiate the graph. You don't need to do this if you're only ever going to use one LLM, but it allows for a little more customization. So we're just going to call, we're using chat OpenAI, so chat OpenAI, and we'll give these a nice JS doc, the LLM to use for the graph. The next we want to use is the next state item is the query. That obviously is not dynamic, or it is dynamic, so you can't hard code that. So the query to extract an API for query string. And these are both required. You can't pass a null or anything because we will be passing them in as the initial values to the graph. But for the next state element, it's going to be the categories. So the relevant API categories, you can delete that too, and this. The relevant API categories for the query. Categories, and this is going to be a array of strings, and each item will be the name of the category, which we can then map to our data set. But since we're not instantiating the graph with this, we also have to allow it to be null. This is because the first iteration, or however many iterations until we eventually reach categories, this will be null because we want to put any data in for it. All right, the next one we're going to want to do is the APIs for category. So the relevant APIs from the categories APIs, and these are not just going to be an array of strings. This repo comes with some types, and these types match up exactly to the schema of our data set. So we're going to want to have this be dataset schema, an array, and of course null because we're not instantiating it. The next is going to be the most relevant API for the query, and this is after our node to select the API. We'll have one API, and that will be the most relevant node according to our program for the user's query. So we'll call it best API, and that will be a singular dataset schema, or null of course. Next is the params for the API call, and we're going to extract these from the query. And if the user does not provide, or if the query does not contain all of the required params, then we'll go through, I'll just leave this open. Then we'll go through to the human in the loop section and actually ask the user for those parameters again. So params, this is going to be that, I think, or null. Let's disable this for ESLint. And this is because we don't know what value. Well, no, I think they can actually always be a string because they're all going to have to be a stringified anyway, so better to constrain it to be a string. And this is just an object containing the key, and that's the param name, or the name of the data. So sorry, let me go back. These can be params in the if it's a GET request and you have query params, you could use these, or it could be passed into the body of the request. Inside of this node, we're going to be doing some mappings and essentially looking in either the body or the required search params and then mapping that to the params here. So we don't need a separate one for body and query params because they're all going to get mapped through there anyway. And finally, we're going to want to have the API response, which is also going to be, this will have to be string any. because we don't know beforehand what the API will return. Next, once we've defined our graph state, we can go and implement the same graph state through our graph channels, but the syntax is slightly different because it's these channels that LangGraph is going to be using. So the syntax for this is the name, so LLM, and then value is null, and this is going to be null for all of these because we're not going to be doing any sort of like concatenating strings or arrays. What you could do for this in LangGraph is if you wanted to say, let's say we had the or let me implement all these underneath the categories just so we don't get out of order. The next one is going to be query. Once again, value is null. But LangGraph does, we're not going to do this because we're always going to return the categories once and not touch them again. But if we were to, say, extract some categories, go to another node, extract more categories, and we want to append it, instead of having to deal with that appending inside our nodes, we can just say value equals a comma b, and these will each be string arrays. I'll fix that in a second. Yeah, so these will each be string arrays, and then you can do a dot concat b, and LangGraph essentially will take, if you return an array of strings via the category key in one of your nodes, it will then use this function. It doesn't have to be this, but it'll be whatever functions in the value, and pass in the existing and the new data. And here we're concatenating it, but you could do whatever kind of operation you want, and it'll return that value to the category state. And let's switch this back to null for now, just because we don't need that. But you can also have a default, which means that right now we're going to default to null, but you could default to, an empty array, let's say. And then anytime you reset this, say at like a checkpoint or on the initialization, it's going to call this default function, and that will be the default value for this channel. But for us, like I said, we're only ever going to be doing null because we're not doing any sort of operations in between each of the nodes. APIs done, best API done, params done, and response done. Now that we've implemented our state and our channels, we can go and we'll start the create graph function. So we can define our state graph saying const graph equals new state graph. And we're going to import this from LangGraph. And this, we can pass in a generic for our graph state, and this takes in an object with channels, graph channels. And now we have new instance of state graph, which we can start adding our nodes and our edges to. All right, to start, we're going to define all of our nodes, and then after that, we'll add the edges. To define a node, you just call graph.add node, and it takes in two args. The first is a key, which is a string, and that's how LangGraph is going to know what node is what and how to route the different nodes to each other. So we'll call this extract category node. Extract category node. And the second argument is a function, which is runnable like. If you're familiar with the LangChain expression language or the LangChain library, you'll know that pretty much all LangChain functions and classes do extend runnables now, except for some of the legacy ones. So you can pass in a LangChain function or any function that takes in at least one argument. The first argument is going to be the state right here. And then the second argument is an optional configuration arg where you can do things like callbacks and tracing. For JS, you don't need to pass that through. We have some magic going on in the background, which can see if you do have tracing, then you don't need to pass through the argument anymore. But since we're not actually going to implement it yet, we'll just define, I guess, the outline, and then we'll go back and paste in the functions later. So we state, graph state, nope, graph state, did I just import something? Yeah, we don't want that. So we only care about the first arg, which is the state. It's going to be our graph state we defined here. And this is going to be a function. And for now, we'll just console log not, if I can spell, implemented, and we'll add the state. Nice. We can kind of copy this outline because the next few will be pretty similar. So next we're going to want to define the get all APIs in category node. We will call it get APIs node. Does the same thing, our key, and then our runnable like function. Next we want to define the select API node. So select API node. Once again, it's the same. The third is going to be the extract the parameters node. So extract params node. Fourth, we can see that routes to the verify all parameters are present node, which will not be a node, but instead it'll be a conditional edge. So we will go and implement that in a second. The third node is going to be the human in the loop. We can see it's conditional edge because we route it is always called after the extract API params node. However, it can either call the human in the loop node or the execute fetch request, and that's because it's a conditional edge, which, based on our logic we will implement, can route it different directions. But the next node we're going to want to implement is the human in the loop. So we'll just call it human loop node. And finally, the last node we're going to define is the execute fetch request node. So we will call that execute request node. Nice. Now that we have all of our nodes defined, we can start to define the different edges. An edge is essentially how you tell LangGraph which node maps to another node or conditional edge. So our first node is our first edge is going to be the extract category to get APIs in category, which is these two. So we can say graph.add edge. It's almost got it, but we don't have third arg here. And this is saying that after this node finishes, always map it to this. Always call this node next, and that's going to be this part. And then we can go and implement this again for get APIs to the select APIs. So get APIs will then always call the select APIs node. Next, the select APIs node will always call the extract API or extract parameters node. And the extract parameters node will always call our conditional edge. So we can now define our conditional edge. This is also going to be a placeholder function that we'll actually implement when we define all of our different edges and nodes. So we can say graph.add conditional edges. The first parameter is going to be the start key, and that's which node will always map to this conditional edge, and that will be the extract parameters node. So once the extract parameters node finishes, it will map to this conditional edge. And the second is a function which defines the actual logic behind the conditional edge. So that also takes in the state arg and a config arg, which we don't need here because we're not making any API calls. We'll add the console log. And then there are two ways you can handle conditional edges. As you can see, there also is a third argument you can pass for the conditional edge mapping. And this essentially says that this function could return, instead of being so from this function, you can either return a string, which is a node name, and then if it's a node name that exists, it'll just map right to that node. Or this function could return any old string or value, and then the third arg would be an object where we say, let's say he returned should always go here. And this is saying that if this function returns this string, then we should always map it to this node. And you can have as many of these as you want. But for us, we don't need that because we're just going to return the name of the node, but it could be a little more declarative to actually define the conditional edge mapping as the third parameter. All right, where were we? So now we define our conditional edge here. That's either going to route to human in the loop. We can define this return type actually, just so we don't forget. So it'll always return either human in the loop or execute request node. Oops. And it doesn't like that because we're not returning a value, obviously, so we'll just change this to be throw an error. And now it's happy with our return type. Because, yeah. And we need to join that one arg there. Nice. Now we've defined this, we can go on and define, do we need any more actually? Let's see. So extract category to get APIs to select APIs to extract params to the mapping. Yes. The last thing we need to do is define our start and end nodes. So graph dot, what's it called? Set entry points, and that will be the first node we want to be called when we actually execute our graph. And then we also want to add a graph dot set finish point, and this is going to be the node that as soon as this finishes, the graph will end, or our loop will end. You can also return a special end variable from any of your nodes, which is just this string. And if LangGraph receives this as the return value from any of the nodes, it will automatically finish it'll exit cleanly. Nice. So now we defined our graph. Once we know this, we can compile it. So we say const app equals graph dot compile, and then we can return app. So we'll see the return type is Pregel. That's just the name of the more lower level LangGraph class. If we go into our main function, we can say const app equals create graph, and then we see if we want to execute it, we could say const response equals await app dot invoke. Pregel also extends the runnable class. You can use the same dot invoke, batch stream, whatnot that you do in LangChain. And this will take in two args that we defined up here, the LLM and the query. So we can also go and define our LLMs. We'll say const LLM equals new chat OpenAI. We're going to want to say model name is, we're going to use 4 Turbo. I never remember the name. OpenAI models. There we go, 4 Turbo Preview. So our model name is 4 Turbo Preview, and then temperature 0, of course. So then we can pass that in as our first arg, and our second arg is going to be our query. I will explain where they came from in a second and what these things are. And then we can see our response. After we wait it, we could, console log. We're going to have to do this later to stream, just a little better UX. But yeah. Ooh, actually, we have this passed in already. Query string. Nice. And then we would simply run this file using the yarn start command from the backend directory, and it would run our graph. Now let me close this. To go over what these things are, essentially from our smaller data set, from the larger data set from Toolbench, they also have a file containing all the APIs and then different queries that I think that they came up with, and then the APIs, which if these APIs were returned from, in their case, Toolbench, in our case, LangTool, it would be a successful run because those are APIs which are valid for that query. So I just went through their data set, found a query which worked well with one of the APIs that we have in our data set, or a few of the APIs, and then I've extracted those IDs from the data set, see the ID, and then we'll add a check here which says that if the best API that was selected has an ID which is inside this array, then the graph or LangTool successfully chose the right tool to use, and it will be successful. Alright, now that we've defined our graph, we can go in and start defining our tools. The first is going to be our extract category node, which we have the kind of wireframe placeholder in here. This is a extract high-level categories class, which extends the LangChain structured tool class, and then an extract category function where the logic will live. This is so we can define a tool which is compatible with LangChain, with a schema, a name, description, whatnot, and then a function which we can pipe everything through and get our string return that we want. So this schema is going to be the, what is it? Describe it given a user's query. Extract the high-level category which best represents the query. That's good. And then we'll name it high level. We'll do multiple. It could best fit more than one category, and then we want to be able to pull the APIs from all of those. So this will be z.array. And inside here, we're going to be using this constant high-level categories mapping that I've already defined, and this is essentially each one of these values is an individual category from our data set, and I kind of passed them all to actually Claude 3 Opus, and I said, given all of these categories, give me 10 high-level categories that map to these lower-level categories. So we will take high-level category mapping, and we'll say it's an array of enums, just so the LLM always returns, if it follows the tool schema properly, it will always return a key to this constant and isn't just making up categories that it thinks fits the query. So z.enum, and then here we just want the keys, object.keys. That's right, and we're missing that, and this type will not match exactly. I remember reading something on Stack Overflow. It's kind of just a weird JavaScript and then fancy Zod typing thing. So we can just cast it. We'll say as string, comma, string. Oh no, it didn't work. Because you can't spread a single string. There we go. And then we need to import this. Nice. So now we have our schema. We'll add some more descriptions for these just to give the LM a better idea. So dot describe the high-level categories to extract from the query, and then we'll describe this enum as well, and we'll say dot describe the an enum of all categories which best match the query. There we go. Kind of saying the same thing 3 times, but it'll work. The name, just give it the same name as the class. And then description, let's actually just use this, and then we don't need to give the schema a high-level description. So description is given a user's query, extract the high-level category which best represents it. Call, we're then going to get the input, which is the type inferred from our Zod schema. We can see that this is just an object containing high-level categories and then a string array. So we can say const categories mapped equals input dot high-level categories dot map category, and then we're going to want to return that. And it doesn't like this, we can say as key of type of high-level category. It thinks that this is just a string, where in reality it's going to be a key of this object because we defined it here. But we have to cast it because this is just going to Zod just returned a string for that. This is a 2D array, so we'll flatten it. Nice. And then we can just return. This call method in the LangChain tool interface needs a string, so we can just return a stringified version and then parse it out later. Return JSON.stringify, boom. And now in here, we'll define our state, graph state. We're going to want to pull out a couple things. We want the LLM, and the query. And since this is the first node, we will only actually have access to these. And now we can start building our LM calls. So we're going to say const prompt equals chat prompt template from LangChain. Nope. Chat prompt template. Remember to import from the different or the new LangChain libraries if available, or else you'll get a warning saying, hey, this is deprecated in 0.2, and we do release it. Those imports will be removed. So import from core, we'll say from messages, and we'll give a system message saying you are an expert software engineer helping junior engineer understand the high-level category of a query. The junior engineer asks you, okay, this is not what we want, but we'll take the first part. Helping a junior engineer understand the high-level category of a query. Given their query and a list of high-level categories, we'll say select the high-level category which best represents the query. And next we can go and define the human message, and this will have two input variables, a list of all the high-level categories, and their query. So we'll say human query, and then a LangChain prompt template variable query, which is just a string wrapped in a single bracket, and then high level categories, high level categories. Nice. Then we can define our chains. This is right. Thank you, Copilot. We're going to want to define our tool first by instantiating this new class, and then we can define our chain. We can say const chain equals prompt.pipe. We're going to want to pipe that prompt to the LLM, and then pipe the response of this LLM to the tool, which actually will not work because we're going to want to parse the output of the LLM first. So we're going to want to define a new model, say const model with tools equals LLM dot with structured output, and the first is going to be the tool, and then this will essentially bind this tool and the tool schema and the descriptions we added to the LLM, so when it sends the request, OpenAI has the actual tool and tool schema available to send that response back, and it'll do all the output parsing, so all we get is high-level categories as the response. So now if we pipe that through here, then we'll be able to pipe that to tool, which we'll call this function passing in high-level categories, which we can see is the same type of the input, and then this will return a string. So this should, return a string, and we're not passing in any generics, so this still thinks it's any. But next we can invoke this. We can say const response equals await chain dot invoke, and this takes in two parameters, the query, right, and the high-level categories. And this, we're going to want to use the high-level categories, but then we'll also include the low-level ones just for some more detail and to help the LLM pick the right ones. So we'll say object.entries.map, and then the key value. This value should be an array of strings. Why don't you like that? There you go. And then we're just going to return high level category, and then key, and then the low level categories beneath that. That's probably good, just calling them low level categories like that. And then this needs to be a string, so we'll have to join them all in the end, and we'll join them with two new lines in between each, just so it's obvious which is an individual category. Why don't you like that? Expected a comma. Makes sense. All right, now we can, this response should be a string, yep, and then we're going to want to parse that to get our categories. So we can say const high-level categories equals JSON.parse, and then this is going to be, what, this is any, right? Yeah, so we'll type it to be string array because we know that's what this is. And then finally we can return it to our to LangGraph, and we'll say categories, high-level categories. There we go, and LangGraph will know to just append this to the state and pass to the next node. So now we can go and replace this placeholder function right there. Let's import it. There we go. And then if we invoke this and look at our langsmith tracing, we should see it call this once and return some categories. So I'm going to add my environment variables. We can come back and run this. All right, so I've added my environment variables, and I'm going to copy and paste something in from a previous project here. And just to walk right through it, we're going to switch this to stream, and then we'll call this stream. Essentially what this is doing is it's streaming the graph. So instead of us having to wait until the entire graph is finished, we can see each node as it gets called. Can add some new lines and kind of a divider. Take the object.keys. If the key is end, then we know the graph is finished. LangGraph will always return that when it finishes. We can log finished, assign this final result variable to the state that it finished with, and if not, then we can just console log the first key of the event, which will be the current node it's on, and like the comment says, if you want to see the actual state of that node on that iteration, you can uncomment that line, and then beneath that, we're saying if the final result is false, then obviously it never finished. And if best API is false, then no best API is found. We will comment that out because we obviously are not assigning best APIs yet. And then obviously it won't actually select the APIs. We'll comment that out as well. Alrighty, now if we go back here and we navigate to the backend directory, call yarn start, and it should start to stream. No, human in the loop is a dead end. Okay. So, where is human loop? Is not there. That's because that obviously won't work. So, let's go back to our graph and see what we want to do with this. Human in the loop should always map back to here, which means that we need to add an edge saying, add another conditional edge saying that whenever human in the loop finishes, we're going to want to call this conditional edge, and we'll pass in the same function here. We'll just quickly define it. Oh, there we go. We already had a placeholder. So verifying params. We can copy this return type here, and then we can replace this. And then we just have to implement it once. Okay, so let's quickly go over what we did. Before, we just had this conditional edge, which said that whenever the extract parameters node finished, it should always map to the conditional edge, which could then either map to human in the loop or finishing. But what we forgot to do is add the edge for human in the loop. So before, it could map to verifiable parameters, then go to human in the loop, but we hadn't added this yet. So now we've added a second conditional edge, which says whenever human loop finishes, we're going to want to call our verify parameters conditional edge, and then that can once again either call human in the loop or go and execute. So if we go back, that should work. Okay, I had to clear my console there because it logged my API key, but we can see that essentially what happened when we tried to run that is it called this category, it executed it, and then it tried to go here and we got not implemented. We're going to update these so it doesn't actually log my API key. Oh well, we're just going to stop logging that because we don't want API keys to get logged again. So if we remove these, there we go back and run it, then there we go. So stream event and then not implemented. And if we go to Langsmith, we should be able to see our LangGraph run. So we started it, called the extract categories node, which called a open API, chat open AI, and that decided that communication and social best mapped to our categories, or to our query, sorry. Nice. And then since we used the with structured output, it automatically parsed it for us, and then we passed that to our tool, which returned the stringified low-level categories from that high-level category mapping. And then it tried to go to the next, and obviously it threw an error. Nice, so now we can implement our get APIs node and the rest. Now that we've seen that, we can go a little bit quicker, just because you guys already have the idea of what how LangGraph works and how this is going to flow through. Alrighty, for the get APIs node, we can just define a really quick function here. We'll say function get APIs, take in the state. What we're going to want to do here is extract the categories from the state. Then we're going to read our dataset file. So const all data equals I'm going to read the file using fs. I'm going to import it from fs, but we're going to use our constant from our constants file, so we actually get the right path, which we can import. And then we'll type this saying dataset schema and array, and then we're going to map through our categories, find the actual dataset item from there, and return it under the APIs field. So we can say const APIs equals categories.map. See, we'll add a check to make sure we don't execute this if categories is false. We can say if categories is false or there's no length, then throw new error, no categories, pass to get APIs node. That's better. Now we can delete this optional and see, and then we can do all data dot filter d dot category name equals c, and then flat that, so we have a single array, and then we can just return APIs. We'll pass that in there, and real quick we can see that this object has, let's say, video and images. If we go to our data set and we search for category name video and images, there we go. So we only have 3 from this category, and there's about 3 from each of the low-level categories from the high-level categories mapping. There we go. And that will return that. And next we can go to the select APIs node, which will perform another LLM call right here. So we're going to pass in all of the APIs which we're able to filter through this node, pass to an LLM, have the LLM select what it deems to be the best API based on the query, return that API under best API. So we can close this, and we're going to want to go to the select API. This already has this class kind of built out. Essentially what this is the same as our extract category tool. It extends structured tool, has a schema, name, description, and this call method. But here we're going to want to define a constructor, because you can see our description and schema is not actually defined, but the type of the schema is. So we'll say constructor, and then we'll super real quick. Okay, so we can see that we want to take in the previous API's dataset schema here, and then we're going to want to call this function to create our description and schema. The reason we're doing this dynamically is because the description, we want the description to contain all the APIs and the API details, and not just say pick the best API. And this way the LM has more context on what APIs it should be picking. So this will take in 2 arguments, so APIs, data schema, and query string, which reminds me, I actually need that there as well. All right. Now that we have this, we can start to craft our prompts. We can say our description, const, I can type again, description equals given the following query by user, select the API which will best serve the query. And then new line, query, another new line, APIs, and then this will be apis.map. There we go, API dot. We're going to want to get the tool name from this. So API is the tool name, the actual. Wait a second. Did I do this properly? Yeah, so that's going to return the individual APIs. This should return if we get one category from this array and not multiple, we should get 2 to 3. That's going to return the individual APIs. Here, we're going to want to, we'll just say tool name API name is going to be the API.API name. This is sometimes kind of funky. It's not always like, if we look in the data set, sometimes it's a path, like a, let's see. Oh, that's an interesting one to pause on. Go all the way up. Yeah, so we can see here API name is like that, but the tool name makes a little bit more sense. So we'll just ignore that. We're just going to want to pass in the parameters, category, tool, API name, description, parameters, and all of that. So we will say tool name, or we'll do high-level category. So, well, no, sorry, they're all going to be the same category. We don't need that. Tool name, API name, comma, description, API description, I think. Is this not typed? Why am I not getting autocomplete? There we go. API description, and then finally parameters, and then this is going to be an array where we will take API dot required parameters and API dot optional parameters. Spread that just so it's all one big array. LLM doesn't need to know what's optional, what's required right now, but it is helpful for it to know the parameters which it takes in, because then if the user's query contains some of that, it can better match the API. And then we'll map over this, map p parameters, and then we will just take the name and description. So we'll say name, p.name, name, and then description, p.description. And then we'll join them all again. Where does that end? Oh man. Okay, there, open, close, open, open, and then there you go, join, and we'll give it 2 new lines. There we go, and just to make this a little bit easier to read, we'll put these all in new lines as well, which means that we're just going to want to have this be a single new line, and then this will be double new lines with some dividers in between so the LM knows. There we go. So now we have the query, which is going to be passed in there. Sorry, like this, it's not a prompt. Then the APIs, and we're going to map over all the APIs that are passed in. And then finally we can return description. So now we can say this dot description equals select API tool dot create description, passing the APIs, passing the query. It'll then set the description to be this nice formatted description. And then schema will be this dot schema, and we've already defined this object. It's going to be an object containing the API, which is what we want the response to be, and then the API will be an enum with the API name. So equals z dot, kind of similar to how we did this, where we have an array and an enums. So z dot object API z dot enum APIs dot map API name, and then describe. We can see describe an enum of. We'll edit this to be the name of the API. Let's make sure we get API name just so it knows that that maps to that. The name of the API, which best matches the query. There we go. Now we've set our schema, we've set our description. Name is going to be the same. And I don't think we do need this because we'll be using it in our call function. So now we're going to assign .apis equals APIs. Boom. Now we've defined our constructor and our static helper function to initialize the tool with the description and the schema containing a dynamic description and obviously dynamic schema of all the different API names that were returned from the last node. And now we can implement this call function or this method. What this is going to do is the LLM is going to take in this tool, it's going to select the API, and then we're going to want to map that to the API that's on the class property, and return that ID, and then we can map to it. Or we can just return the whole thing and then just unstringify it. So we'll say const API, and we'll rename that to API name equals the input, and then we can find the APIs. We'll say const best API equals this dot APIs dot find a dot API name equals API name, and then we'll say if this is false, then obviously something went wrong. So throw new error, API name is not found in a list of API names, and we'll actually add the API names here just so it's easy to tell in the error, and then we can return JSON.stringify base API. Nice, and then we'll just do the same thing we did here, where we'll parse it out. We can honestly just copy most of this because it's all somewhat the same. So we'll copy it, paste it here, but we're going to need to switch up a few things. One, obviously get the state in there, graph state, add our missing imports, rename our tool to be the right tool here, and instantiate that with the APIs and the query. So we're going to want to say, what was the name of it? It was just APIs. Nice, easy, APIs. Pass it in and query. In here, we're going to want to make sure that APIs is true. If it's false, that means the previous node messed up. So we'll just throw an error. So we'll say if APIs equals null or APIs that length is 0, and throw an error, no API keys, no APIs passed to select API node. Nice, that's descriptive. We'll edit this in a second, but we've defined our tool, our structured output with our tool, and it's going to contain the dynamic schema and description. Chain, response, we will add this later. We're definitely going to want to have the query in there. We're not sure what else we want. And then we'll say best API is going to be a single instance of dataset schema, and then parse the response. And then we can just return it. Here we go. All right, to do the prompt, we're going to have a system prompt, and we'll say you're an expert software engineer helping a junior engineer select the best API for their question. Given their, or we'll say query, I guess. Given their query and a list of possible APIs, select the API which will best serve their question. Nice. And then, or their query, sorry. We'll pass in the query, and then we'll pass, we don't need to pass in the APIs because they're already in the tool. Given their query, we'll modify this prompt so the LM has a little more of a pointer towards using the tool. So given their query, use the, where's the name? We can delete that too. Use the select API tool to select the best API for the query. There we go. Let's go over one more time. You're an expert software engineer helping a junior engineer select the best API for their query. Given their query, use this tool to select the best API. Pass in the query. There we go. Now we only need query there. We parse it, chain it together like we did before, and there we go. We've implemented this. We can delete that now. Let's go back. Let's add this to our graph, like so, and import it. Nice. Now we just need to implement the extract params, human in the loop, request, and then we're done. All right, for the extract parameters node, it's a little simpler than the other ones because we don't need to do any parsing or filtering or finding with the tool. So we can just define a prompt, a schema, chain it all together, send it in, get the response. So we'll say, first we'll add the states. We'll state graph state. In here we're going to want, once again, the LLM, query, and the best API, just like that. And next we're going to define the prompt, and we'll say const prompt equals chat prompt template from messages. Oh, why'd that do value again? Okay. Chat prompt template prompts. There we go. From messages, we'll add a system message saying you are an expert software engineer. You're provided with a list of required and optional parameters for an API along with a user's query. Given the query parameters, we'll just say use the extract params tool to extract the parameters from the query. And then we'll say if the query does not contain any of the parameters, we can just return an empty object. There we go. And then the human will say query. We'll change this to be that so we can do new lines cleanly. And then required parameters, required params, optional parameters, optional params. Let's see, you're an expert software engineer provided with a list of optional parameters. We'll add this to the system prompt. Required parameters, optional parameters, query. There we go. Next, we can define our schema. So we'll say const schema equals z dot object, and then params z dot, what is going to be z dot record string, describe the parameters extracted from the query. That looks good to me. Next, we can pass. So we'll use the with structured output method, so we can just pass in our schema. We'll add an extra description here saying describe the parameters from the query, the extraction parameters. Yeah, that's good to me. And then we'll say const model with tools equals LLM dot with structured output schema, and then this should take in a second arg. Where are you? There you go. Yep, config, containing the name, and we will make that name extract parameters. There we go. And now we can chain these all together and execute the call. So say const chain equals prompt.pipe model with tools. We don't need a pipe and output parser because with structured output returns a runnable, which parses it for us, and that's why we can see that this is going to be a object. And then this chain, we can invoke it and get the response. We'll say const params equals await chain.invoke, and this takes in a query, and then also required params and optional params. And now we can build those here. So we'll say const required params equals best API dot required params dot map name description. There we go. Let's see, is there anything else we want from this name description? We'll add type as well. Type, whoops, p.type. All right, and now we can do the same for our optional parameters. And delete that, and now this should just be an object like that, and I believe we can just return because our state has a params field. There we go. Now that we've finished implementing this, we can delete that, and we can go and add it to our graph like so, and import. There we go. Now if we go back here, we can see that we've implemented our extract category node, we've implemented our get API category, our select API, which is going to pick one API out of many, and then we're going to extract the query params. Next, we're going to need to implement the verify all params are present conditional edge, and if all of them are present, we can send it right over to the execute fetch request, and if they're not all present, then we can send it to the human in the loop, which will allow the user to type in the missing params they've had, loop that through until we have them all, and then we can execute the request. So next we're going to want to implement the human in the loop node, which will be the request parameters. This is going to have three functions: read user input, parse user input, and then the function which is actually called by LangGraph. So real quick, I guess we can just do that and then add it to human in the loop like so. Import. There we go. For the read user input, we're going to be using a library called readline. So we can say import star as readline from readline. We can add this here, dataset parameters array, and then we're going to use readline to allow the user to type in their missing parameters. This is going to be we're going to give them an example on the format they should add. So we'll say const params format equals name, comma, value, and then the separator will make it 3 colons name value. So then if they're adding the values, it'll essentially be like this. They'll say, let's say we're missing a city, comma, SF. If they're missing another one, state, comma, California, and they would enter, and that's how we'll parse it out. There we go. All right, now to implement the read user interface function, we can use readline, and we can say const rl equals readline dot create interface. Oops. Oh my goodness. There we go. Input process.standard in, output process.standard out. Nice. And now we're going to want to construct a, actually I could use that. There we go. But this is going to be the const question equals that. There we go. And then missing prompts, or we're going to want to add a string with the missing params. We'll say const missing param string, params.map, name, comma, description, and then we'll join that with some nice formatting. This should be a string, and then we can say, what is this? We'll say LangTool couldn't find all the required params for the API. New line, missing params. That's cleaner. Please provide the missing params in the following format. There we go. And now this is a promise that will resolve once the user enters the params, hits enter, and it'll return a string. So here we're going to want to say const best API equals state. Did we do one before? We need another. So human in the loop, which is what we're doing right now. Extract params. Extract params will always map to verify params. Verify params will then either map to human in the loop. Yeah, so we'll implement verify params first. That makes more sense. So for verify params, graph state, we're going to want to then extract the best APIs. We'll say const best API and params from state. These params will hopefully all be populated from the extract parameters, but if they're not, we're going to need to find the missing ones. So we'll say const required params keys equals best API dot required parameters. Well, first, yeah, if best API is false, we're going to throw. And that's not optional. So now, oops, best API dot required parameters dot map, or much easier, object dot keys. There we go. And now, if we can do this before actually, yeah. So right off the bat, if params are false, then we're just going to want to return human in the loop because we have no params. So return human in the loop. And now we'll actually add a util for figuring out what params are missing. So const find missing params equals required params, and we'll just make this a string array, and then existing params, or extracted, I guess, that's probably better, and that'll also be a string array. And now, given the required parameters and the extracted params, we can map over, so let's see, const missing equals required params dot map p, and then map over the extracted params to see if it's in there. So, oh, this will be filter actually, sorry, not map. Extracted params dot sum e equals p. We'll update this to be required. It's a little bit more declarative, and then extracted. There we go. So map over all the required, filter for params which are not in extracted params, and we want to do .sum and not .includes, because if we do .includes and the required parameter is a string which has, so if our extracted params contain a string that is a subset of the required params, then technically they would be included, but it's not the actual one. So if we do sum and do a strict equals, that verifies that we always get the missing params. That'll return a string, and then we can just return this. So now we can say const required params keys, and then const extracted params keys, object.keys, extracted params, and now const missing keys equals find missing params, required params, extracted params. Here we can say if dot length is greater than 0, human the loop, and else we have all of our parameters. So now that'll work, and now we know that, let's export this so we can use it, and we'll actually put it into a util file, make it a little cleaner, util.ts, utils, there we go. Let's import it. Okay, so now our verified params will always be called after our extract params. Most likely we'll be missing a parameter. We'll have to do human in the loop. We can then, inside our human in the loop, use that util function to find the names of all the missing parameters, pass that through to our readline function, get it from the user, parse it out, send it back. So now const, or once again, if this is false, if params is false, or best API is false, no best API found, that's good enough, I guess. Const missing params equals find missing params, and then const required param keys, best API dot required parameter keys, const extracted param keys, oops, we'll do that, and then this, or that. There we go. Now we have all of these, and then we're going to want to map it back to the actual parameters with the data set parameters here, so that we can get the name and descriptions. So now we'll say const missing params schemas. That'll work, I guess. Equals missing params dot map p, or we'll say missing param name key. Key is better. And then we can find it inside of here. So best API dot required parameters dot find required param, and then we can say if this is not going to work, I messed this up. Object dot keys is not what we want. We want just to map and then get the name. And then we don't want object.keys. There we go. However, we do want object.keys for the param state field, because that's just a single object key value. That's better. Okay, let me fix that over here as well. There we go. Okay, so now to map it back to the full dataset schema, missing params.map, missing param key dot find name equals the missing param key, and then we'll do a filter so it's only the dataset schema. So dot filter, p is undefined, and then we can cast it. There we go. And now we can get the user input. So we'll say const user input equals user input missing params. We'll have to await this. This will be a string. Exactly. We'll add our input here. So input string, and then we can say const, if I can type, const parsed user input equals parse user input. There. Nice. Now to parse user input, we know that they're always going to be in this format, and if they're not, then it'll fail, and that's on the user. So to start, we can say if input dot includes, if it does not include this, you know that they only returned a single missing param. So we can say const key comma value equals input dot split at the comma. string, string, and then we can just return a single object, key value. There we go. And if it does include that, then we'll want to split that. So we'll say const split params equals input dot split, and then we can do the same thing here. So we'll say params split params dot map key value, return that. And it's going to be an array of that, which is not what we want. We'll just do let params record string. Nope. Why'd you do that? String. And then for each instead of map, and params equals spread the previous params and the new one. There we go. And then we'll return this. Nice. So now that we've parsed user input, we can then go ahead and return params, and then spreading the new params and the parsed user input params. We'll also add a log so we can see what's going on. So we'll say console.log, new line, new parsed params, I guess. And then JSON.stringify, new line. We also want this to be a template string, not a normal string, obviously. And null, comma, 2 for better formatting. There we go. And now we have the parsed user params. We're going to return it. We can make sure this is added. There we go. And now if this verify params function determines that we're missing params, call missing params, we'll get human in the loop. You'll be able to add your params, and it can continue on. All right, we have one more function or node to add, the execute request node, which is just going to be executing our fetch request inside this create fetch request file. Here we're going to be doing, not that, that's out of scope for this video. We're just going to be doing create the fetch request, which means we are going to take the state, graph state. We're going to want to say const, what do we want? We want the params. We want the best API. And then we can say if best API is false, then throw new error. No best API found. We don't need to check if this is null because obviously there are GET requests which don't require any parameters. But to craft a fetch request, we're going to want to say, we're going to run a wrap it and a try and catch, just so if this fails, it doesn't kill our whole thing. So we'll say try, and then catch e console.error fetching API. And then if you want to see the actual error, you can uncomment this, but I'll leave it commented for now. Try is going to be, we'll add a variable here for the response. We'll say let response equals null, and this can be any. And then const fetch res equals await fetch, and then the best API.url. The method is going to be method is best API.method. Headers we will add later. We don't, or actually we'll do this outside. Yeah, there are a few things I forgot to do. So some of these API URLs, they're not all formatted the same way. So some of them might contain like /users /brackets user ID /thoughts. And obviously that's not a query param, we can just append to the end. So we're going to have to parse that URL, add in the missing values, and then add any extra query params. So we'll say if the method is get or head, get, comma, head dot includes best API.method. This means that there won't be a body and instead just query params. So we'll say let fetch options equals that. Method will always be there, we know. And we'll drop that. Okay, so if it's a GET request or a HEAD request, then we don't need a body, and instead we can just parse the URL, add the query params, send it in. So we'll say let parsed URL equals a new URL there, and then well, actually no, before we do that, we'll just make this just the string, and then we'll say const param keys equals object.keys params. We'll add another check there saying if. You're right, this is actually a little bit easier. So we can say if we have no params, then all we need to do is execute the request with the URL and the method. And then response equals fetchRest.OK is true. Then response JSON, and else the text. If there are params, then that means we have to parse it out. So we'll say fetch options is like that. The URL unparsed is like that. If it's a get or head request, then param keys, we know this is going to be truthy. And then we can say param keys dot for each key if the URL includes, if URL dot includes a bracket with the key inside here, key, then we can parse URL dot replace the key, and we want to delete it from our params. Delete params key, and that way it's not going to be included inside the search params or the body of the request. And now we have properly parsed our URL. So now we can say let URL, and we'll do this out of here. So we'll say let URL equals new URL here, and then object.keys params.for each URL.search params. And we'll do entries instead, and then key comma value. That's a little bit cleaner than having to do this. And we'll do that up here as well. So object.entries param keys key comma value inside an array, and then if key is true, then add the value and delete params key. That works. There we go. And now we have our new URL, and we're passing it to the URL constructor, the global Node.js URL constructor, because it's really easy to add search params, adding the key, the value. And then finally, if there's still params left over, sorry, we have to do this inside here actually. So then that URL is going to be a type of URL. And then if it's a get or a head request, then we're not going to pass in a body, so we know that the rest have to be query params. So URL equals this new URL that we've parsed out, add the query params. And then if it's not that, then let's see, this actually can go outside because that's not specific to get or head requests. The only thing that is specific to get or head requests is having no body. So now fetch options will equal the previous fetch options, and then body json.stringify params. We need to type this to just be a generic record string comma any, and we will ESLint disable. That's not what I wanted. Disable, we'll add that up here. Nice. Okay, let's go over this one more time. If params are false, we're not going to add in any special query params, so we can just execute it with the request method and the URL, get the response. If we do pass in params, then first we're going to want to parse the URL to see if any of the params belong inside the URL and not as query parameters, which we do here by mapping over all the params. If it does exist, then we add it in and we delete it from the params object. Next, we want to check if it's a get or head request. If it is a get or head request, there can be no body, so we don't need to add a body here. And we're just going to format the URL with any extra query params which might exist. If it's not a get or head request, then we know we need to add the body, so we will do that right here. And finally, we can go ahead and call this again. So now that we have that, and then we can say, we can pass in our fancy formatted URL. I believe we're going to need to do a check here. Yeah, so then else, there we go, because we moved that all out, we can just do const, it doesn't need to be conditional. There we go, nice. Okay, so now body, there we go, and then we already have our method, and we're either going to have a body or not, so we can replace those options. Done, done, and done. Finally, if response is true, then we're going to want to return the response because we have this response key. And if not, then we can just return response as null because we can get a response. There we go. Now we can go back in and, last but not least, add the final node like that. Add our import. We can uncomment these because now we're actually going to be checking if it got the right API and if it includes the right ID. And we can go and run it. So let's clear this and yarn start. We should see it iterate over each node, and it failed. Okay. So we saw that it was able to execute the select API node, and then it failed because it can't parse a empty string like that. So let's see. Select APIs always maps to the extract params node. If there are no params, then we'll make this optional instead. Dot optional. Do not return params. I believe that's it. Let's just really quick, we can go into our Langsmith trace and verify that that's actually the node it finished at. So we see it got all the way down to extract params. It called OpenAI here, and it tried to return that. And obviously, you can't parse that. Yeah, okay, so this should work. If we make it optional, then params will just be that or null. We need to do params equals params null, I believe. What am I doing wrong here? Okay, so we have our params, which has to be record string or null. Extract params is we'll say response and then response.params or null. There we go. Now this should work, and if it picks the same API, then it should. There we go. We are missing number and the phone number we get details for. So we need to provide our number as the name, and the value is going to be a fake phone number. Hit enter. Receive was able to parse the param, but it picked the wrong ID. Okay, but here we can see that the whole loop executed. It was able to select a tool. Actually, there might be another issue. Execute request. We never actually got an error message here. So execute request node, create fetch request. Params are false. No error was thrown. Very interesting. This always has to, so we'll say console.log making request with params, or console.log without params. And then if response is true, return that, else return response null. You've already implemented it. Let's go back and run it. And you can see it's moving quite quickly because we're using OpenAI's GPT-4 Turbo, which is very helpful. There we go, without params. Okay, so here we can see that we have a problem, obviously, because even though we added our number param, it doesn't realize that we have our number there. So now, what happens after human in the loop? Request params. Human in the loop goes to verify params. Verify params is false, then it should return human in the loop. So let's see, let's add a log there. Console.log no params. Actually, we can do this a little easier in LangSmith. So we'll go here. We'll scroll down to our human in the loop node. We'll see that it definitely returned params with a number. If we go to our execute request node, then okay, so it did make a request and it returned it. So it looks like it's just a logging issue for us. I didn't add an API key for Rapid API. All these APIs are Rapid API, so if you want to actually make the request, add your Rapid API key in to the fetch request, you'll get a response. Which means that the actual issue is down here, where we should console log the result. So console.log fetch result, and then console.log final result.response. Now if we rerun, we should see it select this, paste it in, and then fetch result, missing API key. There we go. The only problem is it picked the wrong result, so we're kind of running out of time, but let's see if we can real quick go and do some prompt engineering to get it to pick the right tool. First, we want to see where it failed, so extract category. It picked communication and social. If we go to our constants, go to communication and social, email, SMS, social, communication. If we then go to the IDs, which we're accepting, we can see what categories those are and see if it failed there, if it failed at a further tool. So let's see, category name, data. And it looks like it did not pick the right high-level category. Yeah, so we want it to pick as data and analytics, which means that hopefully if we fix the extract category node with a little bit of prompting, then it'll pick the right high-level category and pick the right API. So I'm going to pause this and I'll come back and explain a better prompt that I added. Okay, so here's the change I made. Instead of just passing in the high-level category, let's go back to the LangSmith. Instead of just passing in the high-level category name and its low-level subcategories, what I'm doing now is I'm reading all of the data from our trimmed corpus. I'm then mapping over every single high-level category, finding all of the corresponding low-level categories in there, and making the string say high-level category, name of the high-level category, and then instead of just the category names of the low-level categories, I'm mapping over every single tool which is underneath that high-level category. And if we look, we can see it's about, what's that? That's like 6 categories per high level. Each of these usually have around 3. So we're going to have, plus or minus 15 tools inside each high-level category. And these tools contain just the name, and that is with hopes that the name is more descriptive and the LLM is able to better select the high-level category based on the names of the tools which are inside that. So we've made those changes. I also updated the this to say high-level categories and corresponding tools, and then the prompt variable name. So if we make that change and execute it, select API. Okay, it's asking for the same parameters, which is not great. Okay, so still didn't work. If we go back to LangSmith, we can see if it picked the same tool or a different tool, or sorry, the same category, different category. Nice, nice, nice. Okay, it still picked the same category, so I wonder if there's more prompt engineering we can do. I'm going to pause this and come back when I've fixed it. Alrighty, a couple minutes later, I made a small but mighty change. What I did is I moved the description. Let's see, I'll copy this and show we had before. So previously, we had this, where I had an expert software engineer helping a junior engineer understand the high-level category of a query. Given their query and a list of high-level categories, select the high-level category which best represents your query. If you remember from some of the other LLM calls we had, we were obviously including the query in the user section, but then more context like the categories, their tools, or the APIs, we would include in the system prompt. So what I did is refactor this a little bit to say, you're a software engineer, you're helping a fellow engineer select the best category of APIs based on their query. You're only presented with a list of high-level API categories and their query. Think slowly, carefully, and select the best category for their query. This was, I added this little prompt engineering tip, which I read in a paper, maybe it was on Twitter a while ago. These LLMs are trained on, obviously, data that humans have put on the internet, so there's a lot of information out there, and let's say courses or whatever, where some human is saying, think slowly and carefully, and get this result. And when people think slowly and carefully, they're going to get to better results because they're not rushing through it. So the LM is able to get better answers. I'm not sure the technical details in that, but it seems to work because it did here. So think slowly and carefully, and then I also passed in the actual context inside the system prompt. So if we go back and run it, then we should see it blow through and select yes. So before it was asking for us for a parameter called number with a phone number. Here it's phone. So let's add in our dummy phone number, hit enter, and then boom, you got the proper ID. Which just goes to show you that a lot of this, all of our code was right. We just needed to modify 2 sentences in our prompt and then move some context to the system prompt, or maybe in a future case it's moving context from system to the human prompt, and then that is able to allow the LLM to pick the right API or for your use case. If we go back to LangGraph, or LangSmith, sorry, we can see that in our open API call, passed in everything there, and it picked 2, data and analytics. Still thought communication and social was right, and if we actually inspect the query, I can see that it's believable. WhatsApp business, check for a phone number for a WhatsApp business account, and that seems pretty related to communication and social, but I'm assuming since we passed in, we search for WhatsApp, then here we go, under data and analytics, there are a bunch of WhatsApp tools, so that's most likely why it's selected WhatsApp. And then inside the get APIs node, obviously we're getting the APIs, and then select APIs node, it selected the proper API because we passed them all in here. And it makes sense that the query is about WhatsApp. It's going to choose the tool which has WhatsApp in the name. And then the rest was the same and it all worked. And yeah, just to kind of reiterate, go over what we did here. We take a user's query, we extract the most likely category from our list of categories based on that query. We then want to extract all of the APIs under that category. Since we're only dealing with 130 total APIs and extracting that way down to under 15 once we get the categories, we can just pass them all in context in an LLM. And this would work up to a pretty large scale now that language models can scale to massive context lengths. But if you're dealing with more than that, you just add more steps to this tree where it breaks down even further. We pass on the APIs to the LLM, it selects one API, then we do some query analysis where we try and extract the parameters from the user's query. We then verify we have all the parameters. If we're missing any, we send that to the human in the loop aspect where we ask the human to provide the parameters, go back, verify we have them all, and then execute the fetch request and get the response. Yeah, that's it. I hope you guys enjoyed this repo. I will push up the finished code on a branch called finish. So let's go finished, add -a and commit finished code, and then we'll lint it and format it just to make it a little prettier. There you go. So now, if you want to follow along from scratch, just pull this repo from main. If you want to see the final code or want to see where you might have differed, then pull from the finished branch, which I'm just going to leave up here. And yeah, I hope everybody enjoyed this, and I hope you have fun building LangTool. I hope you had as much fun building LangTool as I did.